it's a good time to start. Hope everybody's doing well. If you saw the Slack, we have a slightly altered plan for this week, which I put on it. I put there this morning, I think. Yeah, let me see if I can share this. Yeah. Okay, let's see. Am I sharing the Slack? Yeah. Okay. So today we're going to look at. We're going to sort of finish up Chapter 7, the last part of Chapter 7, and we're going to sort of give an overview, a beginning of a look at the Dimensionality Reduction chapter in PCA. And then on Sunday, we're going to do something a little different. After our discussion of gradient boosting last time, there was a lot of activity in the Slack group. You may not have followed it, whatever, but it turns out that, well, it's easy and interesting to take the simple implementation of gradient boosting that Jerome gave in Chapter 7 and extend it so that it can handle the learning rate. And so people tried to do that, and we actually tried to do that in class, but we did it maybe too quickly without thinking too deeply. It turns out if you think more about it, you can get it right. And so Rekil did a lot of thinking about it, and he came up with a nice explanation of what's going on. He also looked at the code inside of scikit-learn. So on Sunday, we're going to lead off with, we're going to let Rekil have the floor for about 20 minutes to give us his summary of what he found out and how to implement a simple version of gradient boosting. It's always nice to be able to implement these techniques yourself so that it won't be a black box to you. And that's what I liked about Chapter 7, and I particularly liked that Jerome showed us gradient boosting, showed us a primitive implementation of gradient boosting, but now we can actually see how to make it better by incorporating a learning rate. That's going to really increase our understanding of gradient boosting. So that's what we're going to start with on Sunday. And then we also have another special talk on Sunday from Salim, who has found this really nice post that was actually hot off the press from yesterday about a software, a package called, let's see, what is it called? Let's see, I just had it open. It's a way to make stacking and boosting and ensembling really, really fast by making use of your GPU.
Rapids, it's called Rapids.
Rapids AI, yeah, it's made by Rapids AI. And so Salim is going to take us through that. It's really interesting. I tried it today, but it's not so straightforward because, well, you can do it in the Colab notebook, but it's not so straightforward to try to do it on, if you have a Windows machine, because you have to have, it actually doesn't run on Windows natively. It has to run on, on Unix. So I tried to get my machine to run it in Docker, but that didn't quite work yet. Anyway, but I can run it on Colab, so that's fine. It makes an incredible speed up when you're doing stacking, boosting, and ensembling because using the GPU to do those tasks really makes them much quicker. So that's what Salim's going to show us on Sunday, and then after that we'll delve more and we'll do the next part of Chapter 8. And then
Joseph, just out of interest, those of people online were FastAI, especially the tabular part. Jamie already has a rough implementation working with Rapids, and he was actually working on it already. So I expect him to be able to release something with FastAI tabular using Rapids as well fairly quickly here.
Terrific. So that means, so FastAI Rapids is going to be integrated into Rapids AI is going to be integrated into FastAI so that you can access it directly. That'll be terrific. What'll even be more terrific is when they get it working when you get it so you can run it on a Windows machine. Because even now with the Unix layer that you have, I forget what it's called, Windows something or other. It's basically the Linux, that you can run on Windows. It's still not good enough to run every feature. In other words, it runs Docker, but the Docker can't, at least I haven't been able to get it so that Docker can completely access the GPU from Windows. And so I haven't been able to run RapidAI on Docker on my machine. So let's start on chapter 7. I want to share the Kindle version real quickly here. Make sure I got it. See, I should have it. Looks like my screen is not behaving. Okay. There it goes, I think. Yeah. Library. Right now yeah, there it is. Okay, so now I'm going to share that. Stop sharing what I'm sharing. Share the Kindle. There. Everybody see the Kindle version of the book? Yes? No?
Yes, we see it.
Okay, great. Thank you. Okay, so I guess actually I want to just share, instead of sharing this, you can follow along in the Kindle, but I want to share the notebooks themselves. So let me get out of this and share the notebook. Share that screen. Let's see now. Display. Share everything. Let's see if I can find this thing. Let's see. I just have too many windows open here. Let's see what we got here. Let's invert. Line summary, data transform. That one. That one. Not that one. Sorry about this. I'll be right with you. There it is. Okay, am I sharing this hands-on machine learning notebook yet? No? Yes?
You were for a second.
It was for a second? Okay, well, let me stop and try it again. Share the screen. And this is the one. Okay, now I should be sharing it, right?
Yes. Yep.
Yep, okay. So this is what we went through last time, the gradient boosting, the primitive implementation. He generated a function that he wanted to fit, a quadratic function with some noise. That's what this is. We might as well just go through it quickly just to sort of get everybody running up to speed. So let's see, why am I not seeing, oh, I'm sharing the wrong thing. I'm sharing from, okay, sorry, I gotta fix this. Okay, now I should be sharing something that looks like Firefox. Can you see a whole bunch of windows here?
No, it's just you on the video.
Okay, I know what to do now. I'm sorry, but I'm going to have it in a minute. Yeah, here goes. Share screen, and this is the one that I want to share. How about now?
Yep.
Okay, sorry, I was sharing the version on GitHub before, which it wasn't a work. It's not a working version. It's just a notebook formatted. So go into gradient boosting. I'm just going to run this really quickly. This example. So we are running the decision tree regressor, and we're kind of running it in a loop. That's sort of running it, and I have iBoost equals, or nBoost equals 4. So we ended up with, each time I printed the residuals output, and the residuals are getting smaller, and finally they go to 0. But that's not, I guess that's not what I want to run now. I want to run the actual code that he had. So this is Jeroen's code, and I'm just doing I'm doing 4 stages of boosting. Or 3 stages of boosting, and then actually 4, because I have stage 0. Stage 0 is just fit the function, the function itself, which is y. Stage 1 is we fit the residual from the first fit, and I started implementing a learning rate, but I actually set it equal to 1, so it's not doing anything right now. And then that's stage 1. Stage 2 is taking the residual from stage 1 and fitting it, and then stage 3 is taking the residual from stage 2 and fitting it. And then we can look at the predictions from all the models, and we'll look at the sequential predictions. Here's the model, the first model where we're just fitting the data. Here's where we're adding the correction from fitting the residual, adding the correction on top of the correction, and then adding the correction on top of the correction on top of the correction. And then we can look at the residual each time and see that the residual is getting smaller and smaller. And you might say, well, why doesn't it get any smaller than 0.05? That's because we added noise of 0.05, going back up here, where we generated the function. Here's where we added the noise. Sorry, not here, but here's where we added the noise. We added Gaussian noise of magnitude 0.5. Let me, participants, I got to mute. Okay, great. I'm not muted. Yeah, so this is the noise. We had 0.05 noise. We're never going to get better than that, right? So we're never going to get a fit that's better than the noise. If you take the noise away, then you can make the residuals go away too. So that's why I think there's something wrong. Oh, well, with what I did at first, we actually, I just want you to ignore that. We actually fitted all the noise. That's not something I want to talk about right now. So we went through, we fitted the models, and now we plot them all. Let's see. Right, so here's the first fit. Here's what it looks like. Well, let's see, H1 of X1. Why don't these two look the same? I'm not sure. So this is the residuals from the first model, and then we add them on to the first model, and we get a better, slightly better. You can see that these red ones are progressively better. Even although the third and fourth ones look similar, but you can on closer look they're not similar. And
hey Joseph.
Yes.
Quick question. I think during the homework review session, we were talking about whether we should use learning rate on prediction or residual. But I think in your case, you're doing it for both, right? I'm
not doing it right now. I'm not doing learning rate. I'm gonna defer that to when we get Rekil to talk about it.
Okay.
Yeah. So right now I set learning rate equal 1, so I'm not doing anything with learning.
Oh, got it.
Okay.
You're just setting it to 1. Got it.
Yep,
okay.
Just like it was in the book. So you can see that each time the residual is getting better and better. And I actually have 4 plots. The fourth one isn't correctly labeled. It should be H1 plus. I should be adding 4 models together here. Okay. Now he shows. Okay, so that's with our own home rolled gradient boosting regressor, right? So now we compare it with, now that we've built our own regressor, we can use scikit-learn. We do that. We do the same thing. And here is when we're using learning rate and we're using 3 estimators, we can see that we don't do a lot better. Let's see, we don't do a hell of a lot better than we did here. with our own version. And then here, when we reduce the learning rate to 0.1, which is, by the way, the default which they recommend whenever you use gradient boosting regressor, they recommend that you use learning rate of 0.1. And remember, the interplay between the learning rate and the number of trees is that if you decrease the learning rate, you're sort of adding smaller contributions from each tree, so you have to have more trees, more stages in the boosting. So here he had 3 estimators, here we had 200. And you can see now that it's doing a much better job of fitting, but there's an alarm bell ringing because you can see that it's trying to fit the noise, which isn't what you want, okay? It's trying to fit the noise.
Just a quick question based on that figure.
Yes.
So actually, your previous statement where you said we are not going below the error of 0.05 because of the noise, wouldn't that be not true? Because basically, if you add more models, you would end up with something like this, right? So it will start fitting the noise, right?
Yeah, but what I'm saying is that the noise in your predictions, if you had a perfect model, if you got a perfect parabola in your model, and then you subtract it from the data, the accuracy is going to be 0.05. It can't be any better.
Right. Yeah, that's what the thing is with, since we're using the decision tree as like the base estimator here, it's not going to give you a parabola per se, right? It's not going to be like a parametric equation like that. It's very, each decision forks off, so it can actually fit each and every point as you go by. That's
right. So if you remove some of the regularization features, you can, and put more estimators, you can eventually get it to fit every point, and have very close to 0 error. But then you know that you're doing something wrong. So,
right, and you should see that on your test set.
Yeah, you'll see that on your test set. That's right.
I'm just saying that.
That's right. That's right, because the test set won't have the same noise. It'll have different noise points, right? It'll have different amounts of noise on each point, and so when you fit the test set, it'll be abominable. That's what you'll find out. That's a good point. Yeah. All right. So so the next thing, this is what we didn't get a chance to go here, but now you can look at early stopping. So let's have a look at this code. We're going to do the same thing with the gradient boosting regressor. We're going to see what happens. We're going to sort of see how you could let it go for a long time, but then back up and find the number of trees that gives you the best fit. So, so we're collecting all the errors, and this is a feature called staged predict. It's giving you the result after. So if you have 120 estimators, it's giving you a prediction after every estimator, so you can see how the predictions go and where they reach a minimum. How the accuracy reaches, or the errors reach a minimum. That's what we're going to look for. We're going to back up and select the estimator that gives us the minimum. That's what we're going to do in this stage. So, so now we're going to look through all the errors. We collected all the errors here, and we're going to look through them and find the smallest one. And then we're going to plot a figure. And here we're going to plot the errors versus the number of trees. And we're going to plot, and then we're going to select the best model, the model at which the error is the minimum, and that turns out to be 56 trees. It plots that model for us. And you can see that it's not as bad in terms of trying to fit the noise as the 200 tree estimator, right? So kind of look at this point here, and look at it down here, and you can see that it's much less allowed to fit these noise points in the data.
Right. So the error is being evaluated on the validation set there.
Yes. Yeah, because we can go back up here and look. So it's
line number 11. Yeah.
Yeah. Why predict? Stage predict. Yeah, we're evaluating. We're doing this on the validation set, right? And so we're sure that we're checking. We got a model that we built, and now we're checking it on the validation set, and we're choosing the best number of trees in order to get a good validation error. So that's early stopping, and it relies on this feature called staged predict, which is a really nice feature of the gradient boosting regressor, which basically stores all the models or stores all the predictions for you at all the for every for every number of trees that you use, for every number of estimators. So remember, I want to just review this. You see this jargon, N estimators, all the time, and they use that in random forest, and they use that in Eta boost, and they use that in gradient boosting. In this case, it's number of trees, so you know, when we're talking about estimators and we're talking about trees, they're interchangeable in this case. All right. Okay. Now there's another feature called warm start, where you can take up where you left off in your last fit. And so now we're gonna actually go through 100. We're gonna go to from 1 to 120 estimators. We're going to get the validation error and look for the minimum. That's what this is doing. And then if else error going up plus equals 1. If error going up equals 5. Okay, so here's another way of early stopping. We're saying if we run this model consecutively with more and more estimators each time, in this case they're incrementing by 1 every time, and then if 5 times in a row we don't get an improvement in the minimum error, then we stop. Does that make sense? That's what this code is doing. So in other words, here they're looking for, if the new validation error is less than the minimum that we found so far, then we set the minimum equal to the validation error for this number of trees, and then we set error going up parameter equal to 0. If not, if we've incremented the number of trees but now we get a worse error than before, then we set error going up, we increment error going up, and then we check for the exit condition. If the error went up 5 times, then we break. In other words, suppose we ran this model and we found that for 20 trees we got a certain minimum error, and then we used 21 trees and the error didn't change, and then we went 22, 23, 24. Now we've had it 5 times in a row where actually you have to go up to 25. We started at 20, we got a small error, but then for 21 trees, 22 trees, 23, 24, 25, we didn't find the error went down. That will cause this condition to be true, and therefore it will automatically exit. So this is a way to implement early stopping based on a criterion that we invented here. We decided that if the error doesn't improve 5 times in a row, then we'll automatically stop. So it's just another way to implement early stopping. So here it finds n estimators is 61, and let's see, did we get minimum? We didn't actually output the minimum validation. Oh, yeah, we should print this out just so that we'll see it. Let's just see what the minimum error was last time. Oops. I did something wrong here. Missing precision. 4F, sorry. There we go. So the minimum error was 0.0027. So let's remember that from this early stopping exercise. Now we do it again, and we've accumulated a minimum validation error, and now it's about the same. It didn't change very much. So it's not very sensitive to the number of trees as long as it's somewhere around 50 to 60. All right. So now we've learned how to use sklearn's gradient boosting regressor. Any questions up till here? No? Okay. Then let's go on. So now there are, actually, I wanted to tell you, I didn't have time to go through this, but there are 3 great implementations of gradient boosting that are not scikit-learn, but you can use them from scikit-learn because they're built with a very simple API that you can actually call them easily from scikit-learn, just the way you called its own native gradient boosting regressor. And one of these is XGBoost, which we'll look at now. And another one, just for in case you want to check it out, is called Light GBM. That's just LIGHT GBM. That's a fast implementation of gradient boosting, and it's faster than XGBoost. And then there's an even faster one with a lot of bells and whistles on it called CatBoost, and that's built by a Russian firm called Yandex. And this is, as far as I know, the best implementation of gradient boosting trees that exists right now. So if you're doing work that requires gradient boosting or regression, or where that's a good model, or even gradient boosting for classification, CatBoost is worth checking into. It's CAT Boost. All right, so let's just see how you use XGBoost. You just import it, and you can see that you build it. You know, you can call it, now that you've imported it, you can call it just like you do the native gradient boosting regressor. It's just called XGBoost dot. So build the model, make the predictions, and I've changed the code a little because I don't like to look at mean squared error. I'd rather look at RMS error. And so here's the RMS error, and I like this. I think that XGBoost has done a good job here because the error, I don't want the error to be much smaller than 0.05. Otherwise, I know that it's fitting the noise. Going back to the fact that we know that the noise is 0.05 for this data set. And in a real problem, you wouldn't know what the noise is. We built this, we simulated, or we synthesized the data set ourselves, and so we controlled what the noise was. And so because I know that the noise is 0.05, I know that I shouldn't get a better value than 0.05 from my model, and something that gets close to 0.05 must be a good model. All right, so now what is the next one? This is just calling it once.
What are the default number of estimators on that one?
You know, I don't know. That's a good question. We can look it up. Let's see, maybe it will show us. Otherwise, we'll just look it up online. Let's see, XGB reg.
I think if you just print that, we should get all the information.
Oh yeah. Okay. So maybe okay. So let me try that first. That might be better.
Hey Joseph, do you mind making the screen zooming a little bit?
Oh, absolutely. I can do that. And anytime that somebody has a problem with seeing it, just let me know. I can do that.
Thank you.
Is that better?
Yep, that's a lot better. I don't have a wide screen, that's why.
Yeah, that's fine. Okay. So now we had XGB reg. That's what we want. So we have to look at this. It doesn't tell us. So what we like to do is do this and then find out what we can get out of this. It's probably got something that tells us the number of estimators. See velocity and jobs and estimators right there. So I should be able to answer Rekil's question. 100. So it took 100 estimators.
Cool.
Yeah. So now, what does this do? This looks like it's going to XGB reg. Oh, it's going to evaluate. Okay, now we're calling it on early stopping, and it's going to do 2 early stopping rounds. And when it does that, I guess it prints out a lot of information. Not sure why there are 32 things printed out, but let's see. See what it does. So it prints out 32 things, and you can see that okay, so it's built-in early stopping for XGBoost is it stops if it hasn't improved in 2 rounds, right? Up above, we implemented our own version from sklearn where we stop if it hasn't improved in 5 rounds. So it's telling us we're gonna keep training until the RMSE hasn't improved, and so
this has 32 trees then, I guess, right?
well, let's see. We'll find out. I guess that's where it stopped. Yeah, that must be it. So it XGB dot estimators. Oops, XGB something or other. XGB reg. Should be underscore reg. Dot n estimators. It still has 100 estimators, but it stopped after 32. Okay. And it gets somewhat similar results as we had before. It didn't get much better. So that's fine. Now, what are we doing here? If XGB, this is just something I did. I wanted to see.
So what was the purpose of the early round step, Joseph, if XGB and estimators doesn't get updated there? You're basically saying train until my validation error doesn't show any improvement in 2 rounds and stop at that point, right? So like
Yes.
in the previous experiment where you stopped at 56 trees,
Yeah.
you could also stop somewhere.
And this time we stopped at 32 trees. So right, so, and that makes sense, right? I mean, if it stops 2 times in a row, but when we're looking for it to stop 5 times in a row, we would have to keep on going, right? The next time
I agree with that. I mean, it should be something less than 100 is what I'm guessing, right?
Yes, yes, and I think your guess is right. It stopped at 32 trees.
No, but when we printed XGB reg n estimators, that throws up 100, so that's why I'm kind of confused there.
Well, it's the original model, right? The original model had 100 estimators, but we ran it in this mode where we're looking for early stopping.
Oh, so now you're saying we would retrain this whole thing by setting n estimators equal to 32?
If we wanted that model, yeah.
Okay.
Yeah, it didn't give us back that model, but it's good that you asked that question because I would have thought it would give us, like you did, I would have thought it would have given us back the best model. Okay, so I'm trying to figure out what I did here. I think I wanted to see the printout. Let's see. It gives us this stupid warning message every time. I'm not sure what this is. Reg linear is now deprecated in favor of reg squared error. So that's fine. I mean, it's using mean squared error, I guess. So let's just run this, see what happens. It's giving us the same string, but I wanted it to print out the error after it was done. So so let's see. Oh, and we got a time. So it's 36 milliseconds per call to this thing. A validation error is it gives the MSE, but I wanted the RMSE, so that's why I changed the code a little bit. Same result as before. This is just a time it thing. I noticed that Jerome's machine is better than mine because he gets it like 20 milliseconds or something. I'm not sure what. Okay, XGB regressor, fit.train. I'm not sure. This looks like the same thing. Oh, now it's 41. Anyway, it's just the same. This is a timing exercise. All right, so that takes care of the gradient boosting part. Now we're going to look at ensembling. We've already talked about it, and I'm going to switch back to the book now. so we can refer to that. First of all, are there any questions about the material we just covered so far? Okay, let's see, I want this. I should be sharing the book now. Everybody see that?
Yep.
Okay, so okay, so here he takes us through XGBoost. We did that, and now we're going to look at this section on stacking. So there's a couple of terms here, and stacking is where you take an ensemble of, you take the classifiers, you get a bunch of classifiers, and you get their predictions, and then you make a new model that uses their predictions as the columns, and tries to predict the data based on the output of those models. So it's kind of like a two-stage model, a stacked model. First, you run the individual models, then you take the output of those models, and those become the features for a new classifier that you then run, and that's stacking. Okay, so that's what he talks about here. Train a model to perform the aggregation, and when he talks about aggregation, he means just like averaging the results. So there's also terminology. He calls it a blender or a meta learner. I guess that's what I just said, is there might be a distinction between stacking and blending. Instead of using trivial functions such as hard voting to aggregate the predictions, why don't we train a model to perform the aggregation? So that's the idea. You take the results, the predictions of all your classifiers, and then you build a new model to weight them and add them together. Well, basically, you figure out the weights of those columns for each of the classifiers. What linear combination should you get to make the best prediction? So it's a linear model. It could be a linear model. And so here's what, let's see, is that the first figure? Yes. So here's several different models. One could be a random forest. One could be linear regression. One could be AdaBoost. One could be support vector machines regression. You take the output, and this just is one prediction, but imagine that this is a column of predictions because you have 50,000 data points. So you've got 3 columns coming out from your 3 models going in, and now you make a new classifier that takes those columns as its features and tries to predict the labels. And that process is called blending. That you're making a model that takes these as its input features and tries to predict the labels. And basically, it's going to find some kind of a linear. It could be a linear combination of these that, in other words, a weighted mean. So this could be, weight 1 times 3.1 plus weight 2 times 2.7 plus weight 3 times 2.9 gives you 3.0 as a new prediction. And again, this is a whole. Think of this as a whole column of predictions. Any questions up to here?
Yeah, Joseph, it's interesting, like, we start with a fixed number of models, right? Like 3 in this case. In the more general scenario, right? Like I might have like 5 or 10 models, right? And there might be there's one more parameter, right? Like there might be a subset of models that might give me a better blend. But he doesn't talk about that in this chapter, right?
That's good. I think you have a lot of experience in ensembling. Maybe you want to talk about that right now. Just say a few words about it.
I just came across a notebook from like a Kaggle Grandmaster. I'll share it here. He just so in his case he was doing classification. And then he ended up with like 40 models.
40.
Right? Yeah.
40 or 4.
40.
40, yeah.
And he was trying to find, okay, what's the if I'm trying to combine these models, like what's the optimal subset of what's the optimal subset? And in each model, he had done like he has done cross validation. So he has a 5-fold cross validation for each of his 40 models, and he just gives one strategy to combine those models, but that's only one way. I'll share the notebook link in both in the Slack and the chat.
Thank you for that, Mehul. I hadn't thought about that. That's a good point. I mean, if you come up with a bunch of models to start with, you have this idea that all these models are good, then there is a problem. You want to pick maybe some of those models don't help each other. Maybe a subset of those models is actually the best one. Now, to start out with 40 models and try to figure out which subset gives you the best answer is an intractable problem, right? Because you have to look at all the possible combinations of subsets of those models. Maybe it's more practical if you have 5 models, right? You can choose all the possible subsets of 4 models, then all the possible subsets of 3, 2, and 1, and then you can actually get an answer. Which subset of those models gave you the best result? Maybe all 5 of them, maybe a certain 4, maybe you eliminate 1.
Yeah.
So that's a really good point. A thought that I just had as I was thinking about this is you could do something like a feature importance thing where instead of being a feature importance, it's a model importance. You could, in turn, you could take each model and scramble the results of the 5-fold cross-validation. Scramble those predictions, and then run that and see what the ensemble got. And then if the ensemble got worse than having all the models, I mean, if the ensemble got better than with all the models, then clearly that's the model you should throw out, right? And you could do that in turn with each model. That's a linear, in other words, if you had 40 models, you'd have to do that 40 times. So that's, that's doable. And then you could figure out like which one should be thrown out. That would be one. So to get an exact answer of which of those 40 models, which subset of those 40 models, that's an intractable problem. But you can advance towards a suboptimal solution by something like what I just said. In other words, you can figure out which subset of 4 gives me the best result.
Okay. Yeah. I think that's a very valid point. And the last comment was like, I haven't, like, when I do things in production, I'm always wondering like all this blending like of these or ensembling of these 40 models, like, do I do it just for Kaggle? Right? Or is it like really useful in production and a real business case? Because in Kaggle, you're going for an improvement of 0.02 or 0.002.
Well, I'm like you. I don't have experience in industry, but I would say that, and you see all these articles on Medium that try to scare you by saying that, oh, if you're good in Kaggle, it doesn't mean you're good in, it doesn't mean you're a good data scientist. And I think that's really bullshit because, the problems that you solve in Kaggle are the most important ones that are, cleaning up data sets and stuff. Kaggle usually has clean data sets. That's the main difference. Then I would say that in some use cases where improving your model by a small amount makes a huge revenue change, it could be that, going for that last decimal place, the third decimal place in your accuracy might be something valuable for the company that you're working for, right?
Yeah. Okay.
Maybe not all the time, but sometimes. Yeah.
Just a comment here, Joseph, that the blending is a model that you're learning, right? So to answer Mehul's question, the underlying hypothesis is that the model will know the blending model will know which one to weigh more and which one to weigh less. That's kind of.
That's a good point. Yeah, because it's gonna, but it won't know that if you throw in 40 models, well, I guess you're right. It would weigh some of the models lower if they weren't good. That's a good point. In other words, if you made this blending model a linear regression, so that it's just a linear combination of these, then the models that were no good or were not helping would get very low regression coefficients. So that's a very good point.
The practical thing, though, to Mehul's question also is, I would imagine that if you deploy 40 models, there are going to be, provided you don't have to do anything unique to the data for all of the 40 models, which in practice, I would imagine not to be the case, that you probably need to fudge with the data regardless of what you're using with one or the other of the 40 models. And that's an overhead that you carry when you do the ensembling or whatever, because if that one particular model were to be impacted as you keep the data updated, as new data comes in, then you'll need to keep fixing every one of the 40 models that break.
Yeah, good point.
Meaning any data that goes into any of the 40 models has to be appropriate, or else it'll break. Whereas the fewer the models, the lesser the number of the fidgets that you'll need to do with incoming data, because it's seldom the case that you don't pre-process the data in some way before you feed it to a model.
Yeah, and when you're monitoring your model in production and you're collecting new data, you have to retrain. If you have just one model, you just have to retrain one model. But if you have 40 models, you have to retrain all 40 of them. I think that's what you're saying, right?
Yeah, and you have to keep them updated. In any one of them breaks, then if you have ensembled all 40, then you're likely to suddenly not have the results that you used to get.
That's a good point. So sometimes it's better to go with something simpler than to go for the best. I mean, like, Mehul raised the question of, you always need to get the most accurate model? A lot of times you don't. I mean, a lot of times, if improving your result by 1% may not even matter. So you might want to simplify things and not try to make the best possible model, because it has more overhead, as Srinivas just pointed out. Okay, so common approach is to use a holdout set. We all know that. You'd have to split the training set into 2 subsets, so that you use the first subset to train the predictors in the first layer back to, I think this is figure 713, isn't it? And then you have a holdout set that you never use until the end when you evaluate things. Oh, this is 713. Okay.
Well,
so
I think it's a little bit more nuanced than that, Joseph, in that he's talking about how to train like the subsequent layers and prepare. You're basically creating a data set for your subsequent layers. I think that's what he's getting at there. I had to reread that a couple of times.
Yeah, I think you're right, Brian. I think normally you just have to create a holdout set for an evaluation set for your training set, but if you're just doing this once, but now you're doing this layered process, so you have to hold out a special set of data that doesn't go into the models. That's what this is showing you, that this special holdout set does not go through the models. It's saved until the end so that you can evaluate. So the models don't get to see this data, and that's how you can be sure that it's going to give you a good estimate of your generalization error. So yeah, this ensures that the predictors are clean. The predictors never saw these instances. Yeah. Okay. Okay, so this is a more schematic, more illustrative schematic. So here's your 3 different models, your 3 different sets of predictions, your blending training set, which is basically these 3 columns of predictions, and then you build a model that uses that starts with these 3 columns and predicts the original data, predicts the original labels, and that's going. Let's see. So this is the 3 columns of data, 3 columns of prediction going into the blender, and then out comes the new prediction. It is possible to train several blenders using linear regression, others. So I think here he's suggesting a whole bunch of different linear regression models, maybe with different degrees of regularization. I'm not so sure what he means here. a whole bunch of different random forest models, maybe using different numbers of trees or different parameters in the models. Split the training into 3 subsets. The first one used to train the first layer, the second one to train the second layer. Okay, so he's talking about layers upon layers of blenders. That makes sense. But I think that what we really ought to do, so here's what he's talking about. Layer 1, you get all your predictions out, and then layer 2 takes predictions from all 3 models and makes a blender prediction 3 different ways. This one blends maybe linear regression, random forest, and I don't know, support vector machines. So it's kind of like a 2-layer architecture. And then a final layer takes these predictions and blends them together to get a final prediction. So here it's getting really abstract, and it really helps. It would really help to have a look at the notebook here. So I'm going to depart from the book, and share the notebook. Let's see. Again, and we'll sort of cheat and go through the exercise here, the voting classifier. It's not really a difficult exercise. So we're just going to basically see how ensembling works and then how blending works. Stacking ensemble. So this first one is voting classifier. So we'll just review how that works. So this is the run up to getting the data. This is MNIST data. We split the data into training. Let's see, train val and test. Train. Let's see. Why are there 2 of these? X-train to split.
Joseph is just going through a 2-step process because he needs to first create or eventually create train, a val, and a test set. So he creates train val as an intermediate,
right? And then he takes
splitting it further down. That's why you have a train val.
Yeah, good point. So first he gets a train val, a test, a train val, and a test set. Then he takes the train val set and further splits it into train and val. So that's how you get this the extra validation sets that you're going to need. Okay, so we're going to import the different models we need. We're going to build all the models. So we've got 4 models. Actually, 1, 2, 3. I tried to do the poly, but it takes too long, so I'm going to take that off. The SVM poly. So we've got 4 models: random forest, extra trees. Remember, this is extremely randomized trees where we take a random split, a random threshold for splitting instead of calculating it by optimization. Then we have a support vector machines classifier and a multi-layer perceptron model, which is sort of a primitive neural network. Okay, so everything's really fast. Well, no, it's not. I take that back. It takes the time. And I shouldn't have done that because I've already trained these models and I didn't want to have to go through here. It takes about a minute or so for each model. But meanwhile, as we're waiting, let's go through the stacking ensemble. Let's just go through the code and see what it's doing. Let's see. So we're just going to go through and get the predictions from each of the estimators that we built above. And then we're going to build a random forest blender with 200 estimators. And that means each tree, each estimator is going to be another tree that tries to fit the data coming from the let's see, random forest blender. Okay, so he runs this, he gets an out-of-bag score. This is a generalization. Remember this, the out-of-bag estimate allows you to estimate the generalization error. Fine-tune it, select the best one using cross-validation. He doesn't do that, but he suggests you could. Predictions, accuracy score. So he built a stacking ensemble and didn't find that it does any better than the voting classifier. which we're still in the process of running. Let's see how far it's gotten. We have, yeah. The problem, which I should have headed off, is that this support vector machines, it takes a long time and it doesn't converge. So it's just, we shouldn't have even used it. But anyway, now we have to wait for it to come to finish doing all its modeling. And I think, let's see. Individual classifiers and groups. So the individual classifiers for the stacking ensemble are going to be the inputs for this this new stacking classifier. So we're basically we're building all of the columns. That's what we're doing here. We're taking, for each estimator that we defined above, that's each of those 4 estimators, we're building a column in xval. So we defined an empty array with the dimension that we want, the number of data points and the number of estimators. So there's going to be 4 columns, and then for each estimator, each of the 4 estimators, we put the predictions from that estimator in a column. That's what we're doing here. So now we have the input for our blender, and now we're going to build the blender. It's basically going to be, it's going to take all of those as inputs and then use a random forest to find the best combination of those that gives us a good result with 200 trees. And the result was 0.9677 as for the accuracy, and that is a legitimate. Let's see. And of course, we fitted on the validation set. So, so this is a legitimate estimate of the error that we might expect. It's still working, but I want to see what the outputs were. Here are the scores that it got from the individual classifiers. The third one is the support vector machines, and it's terrible because it didn't allow it. It didn't have enough time to allow it to converge, so it never got a good result. But you can see that the other results are about, the best result was 0.97, which was for the second model, which was extra trees. Okay, so at the end, 0.97, okay, the voting classifier got 0.97, and as an average, but it was pulled down by this one here, right? So the next step, oh, okay, good, we're done. So let's go ahead and do it. It finished. Now we can get the result. Prediction doesn't take as long as training, so we got the result right away, 0.97. And here are the individual results that got averaged together to give us that result. Oh, why do I only have 2? Because I must have thrown out, let's see, CLF.estimators. Oh, I think I see why. I only kept in 2 estimators. That's okay. It only has random forest and extra trees. That's okay because those 2 turn out to be the best ones anyway. So averaging those together gave us this result, 0.97. Let's see, voting set params.
It's not averaging, right, Joseph? In reality,
you're right. It's taking a combination of those results, right? A weighted combination of those results.
Correct. So
it doesn't necessarily have to be
model,
averaging.
Sorry, I said even if you had a bad model, it won't be weighting it and pulling it down, right? Because it's a voting classifier, the others would dominate and still keep it up.
Yeah, but when you have a bad model, like suppose you have 4 models, one of them is bad, you will do better if you just eliminate the bad one. You might do better if you just eliminate the bad one. Because fitting basically, if you think about fitting 4 parameters, this is simplifying it a lot, but I mean, the idea of fitting a model with 4 parameters versus fitting a model with 3 parameters, a lot of times you can do better with fewer parameters because the model is simpler. But your point is correct. That it's not averaging. It's taking some kind of a weighted combination of those 4 models. In this case,
yeah. Isn't it hard voting?
Because it's hard voting. Yeah.
Default is hard voting. So
that's
it's
correct.
Just saying, and that's where the choice of 2 point. I forget what we remembered what it does when it's even. It defaulted to something. I forget, but.
Yeah, it's defaulting to hard voting. And I made an error here because I had a space there. And so it interpreted this estimators to only include these first 2. So I didn't get the 3rd one. And I don't want to make you guys wait around to see that all. So we'll just go down.
But if you look at cell number 121, you see all the 4 classifiers. I think something else is.
Cell number 121 right there.
Yeah, if you look at what is printed out, you can see all the 4 classifiers there.
Estimators equals, so what? Of course, extra trees, SV. Yeah, so why did it only give me 2 scores? That I don't know. XVal.
Can you just print out voting classifier.estimators?
Print out voting classifier.estimators?
Cell number 297, the last part of your for loop, voting underscore CLF dot estimators.
Yes, yeah, good point. Oops, let's just get that. And then run this. So it only took 2 classifiers. I'm not sure why it's showing. Let's see. Oh, maybe because, no, I don't know. I don't want to run this step because that's the one that takes a long time.
Yes, that's good. I was just curious.
I don't know. Yeah, I don't know why. I'm sure if we run it again, it'll come out fine. I must have done something weird in between. Anyway, so it got 0.97. 0.9713, and it didn't in this case improve over. Well, it's actually worse than the extra trees. So in some sense, this classifier being worse, the random forest classifier pulled down the weighted score. It didn't do as well, which is kind of weird. You would think that you're supposed to do better. And he's trying to show us that, I mean, this example is not a good one because we want to see an example where using the blender does a better job. In this case, it's not.
Probably generalizing better though, right?
Well, I thought this is the generalization because we're evaluating it on the validation set.
Didn't you have an X test also?
Yeah, we do have an X test.
Oh,
I'm not sure we used it. Yeah, I'm not sure we use it here.
Oh no, it's used in the last cell. Okay.
Yeah. Anyway, so let's see. Let's just see what happens if we keep going on. We have all the estimators. Oh, we saw that. 4 of them, and even though I don't want to do that, just make sure I have the same answer there, or we'll have a different answer there. 9713. This is because I'm only including those 2 classifiers. Let's see. Okay, now we change. So what Srinivas was saying is that the default was hard voting. Now we're going to see if we get a better result when we do it with soft voting. Remember what soft voting does? And instead of making a, I guess we take a probability for each classification instead of taking a vote of either up or down. So soft voting, see what happens. And it did, let's see, it did do a little better. Soft voting did, in this example, it did a little better. In the original example where we use all 4 of the different models, it turned out to do worse because that's what he said. He said hard voting wins. But in our case, the soft voting won. Okay, once you have found one, try it on the test set. So this is what Rekil was saying. Now we can look at the test set result. We found that soft was better, so let's try soft on the test set. and see if we get something similar. 9681. So that's not bad. So if our model had been overfitting, we would get a way worse result on the test set, and we didn't. So we're good. I want to try this. Here there's 3, and this is left over from the run I did before where I eliminated the linear model.
You ran a delete in between, Joseph. That's why it disappeared.
Yes, I did. And so this is why I had 3. Now I'm only going to have 2. And so now we run it on the test set for the individual estimators. 0.9645 for the random forest, 0.9691 for the extra trees. And we found that in this case, the voting classifier did not improve our score. We had our extra trees model had 0.9691, slightly better accuracy. I was kind of hoping to see an ensemble that did way better than the individual ones, which I guess I should ask Mehul, because and some of you also have a lot of experience on Kaggle. I don't yet, but so Mehul, have you seen a case when the ensembling just blows away the result of any individual classifier, or anybody?
I don't see it blow away. It's better.
It just improves it a bit?
It improves it a bit. I mean,
I see. Okay, well. Okay, so now we can do a stacking ensemble. And here we're just going to have 2 columns from our 2 models. Let's see, so, why do we have 3? XL and XL. Estimators. I've got a problem here. I don't understand why I have 3. See what happens. 3. Why do I have 3 estimators? Let's see. Anyway, this is a mess. I should run the whole thing again, but I don't want to because it takes like 2 or 3 minutes for each model to run. But anyway, this is the exercise. Well, let's see what happens if I just run it, because it's probably remembering some result that I had before. It'll still give us an answer. So we built a blender out of random forest. Let me just look at this to see. Oh, it's got 3 columns. Okay. Yeah. So we're going to run this. So it's taking predictions from 3 different models, running a random forest model to give us a blended result. And it finished. And it gives us a 0.9683 out of bag score, which is still not too bad. You could add other types of blenders. And that's what they were doing in that last step, where you build a layer from Blender, from a set of different blenders, and then ensemble them together as the second layer. So we could imagine building a linear regression blender. Maybe we can do that right now.
Is the voting classifier your third on top of random and extreme? Is that the reason you're getting 3?
Maybe that's it.
just print out what estimators is equal to.
Yeah, let's do that. No, it's remembering the multi-layer perceptron, because I ran this before, and so it's remembered that. That's fine. So we've seen how to build a random forest blender. We can also do it with another kind of model, just a linear regression. I think, I'm not sure how to call this thing. I think it's just called linear regression. Or does anybody remember from scikit-learn? Okay, learn. Learn, ensemble bagging, regression, linear regression. I don't want the algorithm, I just want the name of the model. Should have put that in my search. That's what I want. There it is, it's just linear regression. I think we've already imported that, so we should be able to do it. Let's see. Yeah. Okay, here we go. Linear regression equals linear regression. I don't think you need any inputs. Oh, maybe just C equals 1 for regularization. See if it works. Linear regression is not. Oh, I think it's linear regressor. Oh, and yeah.
Maybe you need to import it.
Maybe I do need to import it. Okay. Let's see. Where does it come from? Does anybody remember?
Linear models. Linear
model. Thank you. Linear. Is it capital linear or just small linear?
I think it's just small.
Small linear. Thank you. Models. See? I didn't like that. Linear models. It didn't like that. There's something.
Linear model, no S.
No S. Okay. Linear model. There we go. Now what it says.
And it should be linear regression.
It might be regression rather than regression.
Linear regression.
Linear regression. All right. Why is it still? Oh, I see. Linear regression is. Sorry about this. All right, here we go. I still didn't like that. And it got unexpected. Oh, it didn't. I thought that was the keyword, but let's leave that alone then. Maybe it has a default. Okay, and then we can get predictions the same way we did here. Whoops. Insert cell below. Put predictions. X val predictions, Y val, and then I guess we need to calculate the score by hand. Let's see. So we want then sorry, I'm gonna just get the predictions. I should have named this something so that I wouldn't have to run it again, but anyway. It's going to get the predictions out. Oops, X. Oh, sorry, I have to give it the data set. Okay, now I've got the predictions, and I can calculate the error. The original data is let's just see what happens here. Wow, that didn't work very well. So here's a case where, we would probably have to look at linear regression to see what we can do, maybe some regularization or something to help it. It didn't do a good job. Anyway, and you can you can make other kinds of blenders. You can do, you know, the multi-layer perceptron, or there's a lot of different kinds.
This did not do well, Joseph? This is not accuracy, right? We're just getting back an error.
Yeah, this should be very small. So y val is and y. So I'm taking the mean squared, the root mean squared error. So this should be.
I mean, we're actually working with MNIST here, right?
Yes.
So I mean, like I'm saying, just saying that the metric is weird here. We're actually looking for like
10,000. Yeah. Let's see. This is a classifier, right? So, yeah, I've got the wrong error. I was thinking of the regressor that we were doing. This is.
Yeah, I don't think we can use a regressor.
We don't want linear. Yeah, you can't. So what we want is logistic. We want
Right.
logistic. Yeah. Thank you for that.
Also, I think from sklearn.metrics, you can import accuracy score.
Okay, let's do that. From sklearn.metrics.
Accuracy underscore.
That's it, right? Accuracy underscore score.
Yeah, your sklearn has a typo though.
Oh yeah, thank you. SK. There we go. All right, let's see. I want a logistic regression. Yeah, thanks for pointing that out, Raquel. You're absolutely right. I was getting confused between the regression problem we were doing before and this, which is a classification problem. So we got that. You can do this. Logistic regression blender. It didn't like that. Number of iteration. Okay, I didn't like that. Oops, sorry, I didn't want that. Nope. There. Okay, so where are we? Logistic regression blender, that didn't work. We might have wanted to give it a parameter. Total number of iterations. Well, anyway, I'm not sure why this didn't work. But it's, you know, if we had more time, we could actually look into it, figure out what went wrong. There are probably parameters you can, parameters that you can specify that might help it to do better.
Also, that C parameter, you could probably pass it into the logistic regression.
Yeah, that's a good point. So let's see, what parameters are the main ones? C default 1, its default is 1, so it already is doing some regularization.
Here with logistic regression again, can you do multi-class? Or is it just binary?
Let's see, if it's assuming, in the multi-class case, uses the one bird. So it does do multi-class, and you can tell it which loss function to use. But okay, let's see what it does for default. L2 dual false class with random state solver max iter multi-class auto. So it does automatically handle multi-class problems. Yeah. So not sure why it didn't work, but some troubleshooting, we could figure it out. But at the expense of moving on, I mean, I do like to resolve things, but I also like to, don't want to get stuck on something.
That can
so
be
this,
Joseph, to figure it out and post something back on Slack.
Yeah, that sounds like a good plan. Okay, so where are we now? We have a little time to look at chapter 8 on, this is it. on PCA. So he jumps right in. We don't necessarily want to do that, so I'm going to go into the book first. Let's see, stop sharing and share the book. Let's see. Book. Yep. Yeah. Any questions before we jump into chapter 8? We could look at these questions, but I think Wenching will probably eventually do that, right? Wenching, when you go over?
Yes, I'll do that on Sunday because this is an important chapter, so we'll go through every exercise.
Super. Yeah, but meanwhile, before we do that, people, number 8 and number 9 are the only ones that take any time. So I would suggest that everybody try to answer for themselves all the way through chapter 7, even if you don't, it'll take you like maybe 5 or 10 minutes to come up with these answers. There's no work to do, really. It's just thinking. And then if you have more time, you can run through 8 and 9, and the ones we just ran through today in the notebook. But yeah, it would be good to go through 1 through 7. Spend a few minutes. Don't just wait for Wenching to tell you the answers, right? Okay, let's go to chapter 8. So this is an important chapter, an important area of machine learning, because a lot of times you have problems with a very high number of dimensions, and that can slow you down in your, your models can be slowed down when you have lots and lots of features. If a lot of those features can be thrown away without too much impacting your accuracy, then that can sometimes be a good thing to do. If losing a % or 2 of accuracy isn't that important, and you can get a trade of a 10 times reduction in execution time or something like that, it could be a good, dimensionality reduction could be a good thing. So we're talking about reducing the number of features. We've already seen a little bit of dimensionality reduction. Remember when we talked about the lasso regularization method, where we're adding together the absolute errors the absolute sizes of the absolute values of the weights. Remember, and that tended to reduce some of the weights to 0, and that's sort of like a de facto dimensionality reduction, because you actually, if the weight becomes 0, that means you've basically eliminated that feature. So now we're going to do more of that, a more general study of dimensionality reduction. And he also mentions that it's useful for data visualization. There are, I don't think we studied it in this chapter, maybe he studies it later on in the book, but there's techniques for taking large numbers of dimensions and mapping them down to 2 dimensions to allow you to actually visualize what's going on in an understandable way. So that can be very useful. You can imagine if you have like 10,000 features and there's a nice way to visualize it in 2 dimensions, then that can be a really valuable thing. There is a common package that do that. The name of it is escaping my mind. Does anyone happen to know the name of that package? It basically reduces your dimensionality to 2 and helps you to display high dimensional data sets. I think it starts with a T, but I can't remember the actual name.
His
Yeah,
name?
that's right, TSNE. That was invented by Geoffrey Hinton, and it's still commonly used. Yeah, TSNE. And I think he might talk about it later on in the book. Let's see. So now he talks about dimensionality. Don't ask me about this one. I don't know what the hell this is. Four-dimensional space. No one can visualize a 4-dimensional space. So here he's talking about 0 dimension. 1 dimension is a line. 2 dimensions is in a plane, and 3 dimensions lie on, a cube takes 3 dimensions. But he makes a point that that as you go higher and higher dimensions, more and more of a greater and greater fraction of the data of random samples will be close to an edge. And he says that for a line, for a line segment, you can see that if you take a data point, if you randomly choose a data point, only a very small, if you make a 100 random data points between 0 and 1, only a very small fraction of them will be near the edges. If you take 100 random data points on a square, the fraction of the points that are within a certain distance of the edge goes up. And again, for a cube, it even goes higher. And he actually has numbers for this. He talks about in a square, it will have only 0.4% chance of being, and now I've lost, of being located less than a distance of 0.001 from a border. Whereas in a 10,000 dimensional hypercube, the probability is almost 99.9%. That's kind of hard to visualize, but what we could do is we could actually do this for a square and a line and a cube, maybe, just to convince ourselves that it does get that the percentage of points near the edge does get higher. So let me slip out of this thing and go into a notebook. Let's see, stop share, new share, go back to that notebook. So you now should be seeing the dimensionality reduction notebook. I'm gonna build something. I don't think this will take too long. Let's see, we can build our linear sample equals 100. Well, we can draw lots of points. I think I have to import, does anybody remember the magical incantation for importing the random number generator? From random import random.random, I think. Does this ring a bell? We'll see what happens now. I didn't like that. From random, from sklearn.random. sklearn, random. It didn't like that. Import random dot. I thought. Okay, maybe it wants that. Does anybody remember the magical incantation to get the random?
Or
pardon?
np.random numpy is very important.
Oh, we could do it from NumPy. That's great. Let's see. Let me move this bar out of the way. All right. We don't need that. So yeah, that's good. Well, let me just call this sample. Let me just call this x1. x1, and we can take x2. So I'm going to get, I'm going to do up to 4 dimensions, or I'm going to do up to 3 dimensions. So let's do, sorry. So I'm taking samples of points. I'm sampling points. I'm sampling 10,000 points between 0 and 1. I think that's what this is going to give me. I think this is just uniform, right? np.rand. It's just a uniform random deviate.
Yeah. I think
okay,
you
so,
random in middle, numpy.random.rand.
Yeah.
Random.rand, right. That's what I want, is a uniform deviate. All right, let's do that. And that. And now I'm just going to count the number of points that I got. For a line, I can say, okay, I can say that distance equals 0. Let me say 0.01. And I'm going to ask for how many points do I get the distance? Let's see, n1 equals x1 less than, x1 less than distance. And n2 for a square, I want x1 minus x2 squared, x1 squared minus x2 squared, and I want the square root, just a Pythagorean theorem. And that's going to, and so then I can count, or sorry, I'm going to count the number of points, right? So this is the number of points in a square that are, this is not what I want. I got to, this is not what I want. I want, it's a little more complicated. I want the distance of the points from the top and bottom. Well, this is going to take a little more time to code than I thought. But let's just look to see what we got here. We should be able to figure out. So 75 out of 10,000 points are close to the edge, are close to 0. But I also, let's see, x1. I also get to include the other end, the x equals 1. So I can also go x1. I want absolute value. This doesn't really matter. So I want the distance from the left edge, which is 0, or the distance from the right edge to be less than. I want to allow that to happen also. Or absolute value of x1 minus 1. X1 minus 1 is also less than distance. So this is just for a one-dimensional case. Let's see, is this going to work? Let's see if that worked. Nope, it didn't like that. It tried to do, so I have to do this. I think I have to do this to make it work. Let's see. I got it. I think that's going to work. Yeah. So allowing, so what I have here, N1, I'm looking at the points on the line segment that are near the edges, right? Near 0 and near 1. And I found that 185 out of 10,000 points, which is like a few % of the points, are near. I don't know if he did the calculation for a line segment, but if he did, we could compare our result. For N2, we get to look at the corners of the square, between 0 and 1, the square that's in the first quadrant, right? The unit square in the first quadrant. We could ask for the number of points that are near any of those corners. I think that's what he's doing in, or is he asking for the number of points that are within 0.001 of any edge? I can't remember what he's doing. But you could see how to code that up, and you could verify the numbers that he got. And all we're doing is using, in 2 dimensions, we'd have to use the Pythagorean theorem to get the distance. In 3 dimensions, we would just use the extended Pythagorean theorem, which just has 3, you take the square root of, x squared plus y squared plus z squared, and that's the distance in 3 dimensions. So I thought I was going to be able to code this up really quick, but it takes longer than I thought.
Yes,
Yes.
the easier way, Joseph, is to think of what number of points in a given dimension, as we change or increase the number of dimensions, lies within a certain fraction of distance from that point. That at least is easier for me to recall and remember, which is in a single dimension, if you say 10%, you want a point which is within 10% of some value, let's say 0.6, then it's 0.55 to 0.65. Then you increase it and you give two two-dimensional points, X and Y, and then you change each, and each of them could be independent value. And again, each of them is within 10%. And if you keep increasing, you go to 3, and then you go to 4, and then you go to 100, you'll find that, and in fact, it's illustrated by, so, the kind of parallel example is how many points would you find in very high dimensions, which are within 10% of any given point, and you'll find that the space becomes sparser and sparser as the dimensions increase.
Right. That's what he's talking about in this chapter. But I was trying to do some specific examples because he goes right away from 1 dimension to 10,000 dimensions, and I think it's easier for us to visualize 1, 2, and 3 dimensions, and then we can generalize to 10,000 dimensions. So yeah. I think he was asking, I believe the problem, so the problem we just solved was what fraction of points are within 1% of the edges of a line segment. That's what we just solved. And we found that it was
point, Joseph, 1% from the points, right? In your case,
in this case, it's the edges of our structure or points. But in 2 dimensions, I believe he goes on to talk about the number of points that are within 0.001 of an edge. I think he wasn't just talking about the endpoint, the corners. Is that right? I don't have the textbook open, but I think he was talking about distance between an interior point and an edge. Is that not right? Or was he actually talking about just the distance between the corners? Does anybody, can anybody find that in the text? Because I don't have it open right now.
He talks about the probability of any random point in a unit square being located less than 0.001 from a border.
From a border, that's right, yeah. From the edge. Okay, so that's why it's going to take longer to code that than I had anticipated, because I was thinking of just doing it for the points, but we have to do it for the borders. So yeah,
it's equivalent though, Joseph. What you are trying to do. In fact, I have the thing pulled up because there's an equivalent problem which illustrates this better in the introduction to statistical learning with R. And there is an equivalent question posed in one of, especially with K nearest neighbors, because you can see this becoming a problem with K and N at very high dimensions, because none of the points are close to any random point you choose, because as your dimensions explode, the points all go towards the extremes, right. And that is an equivalent situation. And there's an easier way to conceptualize what he tries to explain. I can pull that up if you want, but I'll need the screen to share that.
Okay, all yours.
Okay, can folks see my screen which says local approaches high dimensionality?
Yep.
So this is where the equivalent problem, it's not exactly what he's talking about, but it makes the same point. Suppose we have a set of observation each on p equals 1 feature that's x, and we assume uniform distribution, and then we try to predict a response only using points which are within 10% of the range. So then you say 0.55 to 0.65. So the question is, on average, what fraction of the available observations will be used to make the predictions, right? So if you're within 10%, it's 0.05 and 0.95. So uniform, you can read through it, but bottom line is you'll kind of use 10%, because in one dimension, if you're within 10%, that's what it is, it's 10%. And if the data is uniformly distributed. Now let's go to the dimension 2. Now we have 2 features, x1 and x2, and each of them are uniformly distributed on 0, 1, 0, 1. And now we wish to predict a test observations response using only observations that are again within 10% of the range of x1 and 10% of the range of x2, closest to that test observation, right? So in each of the 2 dimensions, we want points which are within 10% of x1 and 10% of x2, where x1 and x2 kind of indicate the 2 dimensional values of the point. On average, now the question becomes, what fraction of the available observations will we be able to use to make the predictions? So it's the same, but it's in 2 dimensions. So if we use observations within 10% of the range of x1 and also within 10% of the range of x2, then what fractions of the training observations are used to make the predictions? So we can use the same logic, but assuming, and here we make the assumption that x1 and x2 are independent, then obviously the probabilities of these 2 events are, each of them is 10%, so each is 0.1. So it becomes 0.1 square, which is 1%. So you already see that from going from 1 to 2, 10% of the overall uniformly distributed points are available in 1 dimension. In 2 dimensions, it's 1%. And if you carry the same logic forward, then we see that if you ask, there are 100 dimensions or 100 features, again, assuming that observations are uniformly distributed, you want to predict the test observations response using observations within 10% of each feature's range that is closest to the test observation. Again, what fraction is available? And using by induction the same logic, we find if you want to find 10% of all P for where P is equal to 100 features, then it's 0.1 to the 100. So it approaches 0. So that essentially says as you explode, the number of points within the 10% of your choices of points just approaches 0 as the dimensions grow large.
Right. So everything gets sparser in high dimensions.
Exactly.
I think,
so,
yeah.
So sorry. So he just says, you know, a p-dimensional hypercube centered on it, and then you can go on to indicate that how much of the data is on average available for p equal to 1, 2, and 100. What's the length of each side of the hypercube? And it's a different way of calculating. And for a 100-dimensional cube, and you'd see that, you know, 97.7%. So in order for 10% of the training observations to fall within, each side of the cube must extend further and further into the range of the dimension. This is another way of explaining the same thing, that all the points are close to the edges of your cube.
All right. Okay.
Okay, that's it. And I'll post the link to that.
Thanks, that's great. So that's from the Introduction to Statistical Learning?
Yeah, it's actually a solution to one of the questions of its chapters, but it conveys the concept much more, at least to me, easier to grasp than what he tries to explain with the math.
Mm-hmm. Okay. Okay, let me go back because I think it's not as hard to do this problem as I want. I want to do the problem for, we did it for the straight line. I want to do it for the square and the cube. And I think that it's not as hard as I thought it was. So let me see if I can do this. Got to find my Zoom window first. Just lost it. Where's my Zoom window? Oh, return to meeting. There we go. Share screen. Back to what I was sharing. Okay, so this is kind of like the reverse of what Srinivas showed us. He showed us that the points are getting, you know, at any random region, in any specific region in this high dimensional space, the points are getting very, very sparse. And they're sparser and sparser with the number of dimensions. And sort of the other side of the coin is that Why is it getting so sparse? It's because most of the points are concentrated near the edges, it turns out. So that's kind of very counterintuitive. So that's why I thought it would be interesting to actually show this. Can everybody see now we're back to this notebook that we were sharing before?
Yep.
Yes? Okay. I'm gonna, I think all I have to do, I don't really have to calculate Pythagorean theorem distances. I just have to use absolute value distances in one dimension because we're looking just at edges. So I think this will give me what I want. Let's see, and I can, let's see. I already have it printing this. Sorry. So this is for a straight line, a line segment. I've got it for a square. I think I do. So let's see if that worked. Yeah. So 411 for 2 dimensions, and then I can do the same thing for 3 dimensions. It's just a bunch of, let's see, all I have to do is add another one of these in there for N3, for X3. I'll explain what I did in a minute here so that it won't be so obscure, but I think this will be it. Oops, something went wrong. And Python is not callable. What didn't it like? Oh, okay. I must have made an error in the implementation here. So first I have this, then I forgot to put the or in between. Now that should work. Try again. Yeah. So you can see that the fraction of points that are near the edge, and by near the edge I mean within a distance of 0.01 from the edge, right? You can see that it's the fraction of points near the edge is increasing as we increase the number of dimensions, right? With this method, it would, I can keep extending it, but to do a 10,000, I'd have to change it. I'd have to refactor the code to make it easy to do 10,000. But the point is, you could keep going, and you could look at, you could look at adding another one, just to convince ourselves that it goes up when we add.
Didn't the points increase, Joseph, from 400 to 611? Shouldn't it have reduced?
No, we're talking about the number of points that are near the edges, and that's what increases. And remember, he said that when you get up to n equals 10,000, the fraction of points near the edges are over 99%.
And how is this? Yeah, like I think Gautam has also mentioned this on the board. If they are uniformly distributed, why are we talking about some points being closer to the edge and not being uniformly distributed within there?
They are uniformly distributed, but the dimension has increased, right? So the points are uniformly distributed, but now a greater fraction of them are close to the edges of our structure.
If it's
as we go up in. Yes, it's uniformly distributed in, when we look at one dimensional, we're looking at points that are uniformly distributed on a line. When we look at 2 dimensions, we're looking at points that are uniformly distributed on a square, etc. Right? So the distributions are uniform, but we're finding that a greater and greater fraction of them are near the edge of our structure, in the sense that they're within 0.01, a distance of 0.01. That's what I mean by near. Within a distance of 0.01 of one of the edges, right? And
Sorry, the key thing that I had to get my head around, Craig, Gautam, is the fact that they are uniformly distributed along each dimension. But when viewed in the totality of the dimensions, it results in each of these points being much closer to the edges as the number of dimensions explode, which is what is counterintuitive. That's specifically why he says this totally counterintuitive. Because in fact, if you look at the calculations he has done subsequently, he shows that the average distance between points which are supposed to be within a unit cube comes up with a number which is in the hundreds.
So basically, as dimensions increase, we are kind of talking of the intersection, like how you were multiplying with the example from ISLR 0.1 into 0.1 into 0.1 into 0.1. So as the dimensions increase, we're kind of trying to look at this intersection of points that are kind of close. See, I understood with K and M, but here I don't know. It's making hard.
But that's I mean, if you grasp, that's why to me it's much better explained with through the KNN route, because it's counterintuitive to begin with, and eventually you get to the same point that even though points are uniformly distributed along each dimension, as the dimensions continue to increase, you find that exactly what Joseph said, which is, you know, whatever the number, very high number of points are close to the edges of that, whatever shape in 100 dimensions you have.
I want to, let's see, I want to go over before I want to make sure that everybody understands what I've done here. So I've defined uniform points on in 3 dimensions, right? And I've used them, I've sort of used them more than once, but it doesn't matter. I define a distance that I'm talking about, and this distance means, this is what I mean by when I say near. So I'm defining a distance of 0.01 to be, when something's within 0.01 of an edge, that's what we mean by near. So now we're counting the points that are near an edge. And for a one-dimensional line segment, this is how we can count them, right? We require that these are our points in one dimension. We want the points to be either within 0.01 of the point 0 or within 0.01 of the point 1. So this gives me a Boolean variable. It's basically an indicator that tells me whether each point is close to the edge. So I have to add them up. If I add up the Boolean indicator, that tells me the number of points that were close to the edge.
Sorry, Joseph.
Everybody, yeah.
Yeah, so there, when you say edge, you're actually just talking of the points 0 and 1, right? So 0.
In one dimension, right, the edges, the edges of a line segment are points, right?
Okay.
Yeah, so in one dimension, the edges are points. In 2 dimensions, when we're dealing with a square, I had the picture up, but now I lost it, but I can draw it again. But let's see, annotate. Yeah, in 2 dimensions, we're talking about a square, right? So we have a unit square. And so now we're asking for all the points that are located, you know, within the border, you know, that's 0.01 away from an edge. I'm sorry about my bad drawing, but I mean, the point is we're looking for all the points within this region, right? And that's what I claim this is doing. Okay, let's see, get back my pen. Give me back my pen. There it is. Yeah, so that's what I claim that N2 is, right? I'm allowing the points to be either the x coordinate. So this is so now x1 is the x coordinate of the square, and x2 is the y coordinate, right? So I'm saying that x1 can either be within 0.1 of x equals 0, which is this vertical line, or it can be within 0.1 of x equals 1, which is this vertical line. That defines some of the points. And the rest of the points are the x2. We can have points. So that defines these 2 regions, right? The first line, right? This part of the code counts up the points within these regions. Does that make sense? All the points that are within 0.01 of x equals 1, of the vertical line for x equals 1, and all of the points that are within 0.01 of the vertical line at x equals 0. So this counts those points, but now I also want to count these points. And so that's the second part of the statement. So I have or, y can be close to 0, y can be within a distance of 0, or y can be a distance of 1, within a distance of 1. So that counts these points. Does everybody see that so far? I hear silence, so that doesn't mean, that doesn't give me confidence. Are there any, can anybody ask a question if it is not clear? Well, maybe some people are shy. I'll just look on the chat and see what they're saying. 3 times along edge, blah, blah. Yeah. Well, anyway, so the third thing, so I guess, so this tells you how many points are near the edge of the square, okay? And then you can imagine a similar construction in 3 dimensions, counting all the points that, and we're adding on the points such that z can be, the z coordinate, the third coordinate, can be within, can be close to 0, close to z equals 0 or z equals 1. And that's what this last line is, right? Sorry.
Shouldn't there
So
be
I've
more
added,
dimensions in that one, Joseph?
pardon?
Shouldn't there be more dimensions in the N3 scenario? Because you would have like 6 different planes, right?
Yeah, but
Or you take every combination of x, y, z, where you hold z at 0, then z at 1. Wow.
well, there are 6 edges. There are 6 edges to the square, to the cube, right? The first line is going to capture 2 of the edges. It's going to capture the edges that are parallel to the that are let's see, perpendicular to the x, to the line, to the x-axis, right?
Mm-hmm.
The second line here is going to capture another 2 edges that are let's see, that are perpendicular to the y-axis, and then the third line is going to capture the third set of 2 edges. So I think this is correct, but we can think about it more. If you know, I'm like 95% sure that it's right, but we can think about it in between classes, and if you come up with a reason why it's wrong, let me know. But the logic, I'm just extending the logic that I use for the square, right? I only had to count, the square has 4 edges, and I count 2 of them with the first line and 2 of them with the second line, right? I mean, 2 of them with the first piece of the logic, and the other 2 with the second piece of the logic. And so I think this is correct. It correctly captures all the points that we want, right? And then we can go on and do N4, but I think the point is already made. So, and then you can write a fancy, anybody that wants to can write a fancy code and extend it to do 10,000 and see if we can replicate Jerome's result. But anyway, so the point is that the higher dimensional space, the higher the dimension of the space, the higher the fraction of points are near the edge, And this is complementary to what Srinivas showed us, and I think it's important to understand both things. The points are sparser, that's what Srinivas showed us in high dimensions, and they get exponentially sparse and it goes with the number of dimensions. And we're also seeing that the points are, a greater and greater fraction of the points are near the edges for higher and higher dimensions. That's the thing that Jerome is showing us, and I think they're both complementary, so it's good to see them both. Yeah, so are there any questions as to that? All right, well, in that case, I don't want to go over, we'll just stop here, continuing on Sunday, and we're going to hear from Rekil, and we're going to hear from Salim, and then we're going to hear from me on going further into chapter 8. We'll actually start discussing SVD.
I have a question.
Yeah.
So in KNN, is it right if I say that the suppose we have a point of interest. That point might be, and we have really high number of dimensions, and our point of interest might be somewhere in the middle, far away from the edges. Is that why KNN does not work?
That's why KNN gets harder and harder as you go to higher dimensions, because you have fewer and fewer samples. And this is what Srinivas was going through. Let's say you wanted to have a certain fraction of your data points in your sample. And so in higher and higher dimensions, the points get so sparse that if you ask for how many points are near this point that I'm interested in, it becomes really close to zero, or within a certain distance of this point, it becomes zero. It's what you said. I mean, things get sparser and sparser. And
but it is possible to have points in high dimension that are far from the edges, right?
Yes, it is. Yes, it is. It's just that they're very sparse. As the dimensions go higher, they're harder and harder to find.
That's kind of the confusing thing for me. Like with KNN, we are saying, I understand, like if you have a point in a really high dimension and you're trying to basically find n closest neighbors, k closest neighbors, but then it's just that this number is really small. But then on the other hand, we are saying that we have 99.9% of the points which are close to the edges. So hence KNN should not suffer, right? Because you're having those 99.99% of your points so close by.
No. It isn't saying that. It's saying that for any random point, if you were to choose, which you would choose anywhere, then it's not at all a given that any other point would be close to it. So that's why
that's what. So the contradiction there is,
you drew from going to the 100 and let's stick with 2 dimensions and 100. So in a 100 dimension space, the amount of space that you would need to cover, or the amount of that 100 dimension space that you would need to touch to just get to the same 10% delta from any given dimension is almost 99 point whatever. You can calculate it based on the same thing I showed you, 9999 something of the total volume of, of that dimension, which if you reinterpret it says that those points are lying only on the remaining edge, if you will. So it's as Joseph was saying, it's kind of the complementary thing that when they are so sparse and you have to get to even 10%, you have to encompass so much of that space. What you take away is the fact that the points are lying close to the edges.
Correct.
Of
So
each of those dimensions.
So is it right if, yeah, go on, sorry.
No, just going off that same question, Gautam, so Gautam mentioned the point in the center, right? So now we are saying that the points in the center are very few.
They're sparse. So if you're doing a problem with KNN and you want to have points that are close, in other words, you need neighbors, you need near neighbors. So you say, I want only the points that are within a distance of 0.1 of this guy, of this point that I'm interested in. Well, you may not get any in a high dimensional space.
Correct.
That's the conclusion that we draw.
If that point is in the center, right? But then going off Jaron's explanation on that argument, we are saying 99% of the points are on the edge. So if you were to pick any of those points and perform KNN, you wouldn't have this problem.
Correct, but in general, the points on the edge aren't the ones that you're interested in. You don't want to restrict yourself to the edge. Your point is going to be anywhere.
Assume you're just randomly picking a point.
Yes.
And 99.99% of the time, it would be close to the edge, right?
Yes.
You're just randomly picking a point.
Yes. But
so
what that means,
close to the edge, right?
What that means is that you're not sampling all of the space very well. If you're just going to rely on that sample, you're going to end up preferentially with points near the edge. And so your model is going to give you skewed results.
That's what we just proved, right? If you just pick any random point
yes,
in a 10,000 dimension space, 99.99% time it would be close to the edge.
Yes.
So KNN would still work, right? Because most of the time your point of interest would be close to the edge.
Not necessarily, because you could, first of all, by limiting yourself to points on the edge, you are skewing your model because you're not
But it
sampling the
should
whole
work
space.
99.99% of the time, right?
I'm not so sure about that.
So-
I'm not so sure of that. I mean, I've done problems
Why
with
not?
KNN. I've done problems with KNN, and they, and I need to have certain points. You know, I've done 5-dimensional problem, and I needed to have certain points that I didn't know were near the edge, or they may not have been near the edge, but they were needed because they were they were the points that I needed to find out about. And so it wouldn't have done me, it wouldn't have, well, KNN didn't do as well as other models could because it was not sampling the space as well as it needs to be sampled. I don't know. I mean,
Gautam, the fallacy is that you're saying that I'll pick the point in when the data is given where those points lie, you don't get to choose. They randomly are given depending on your data. So that's why, at least for me conceptually, if you read the rest of what the link I posted, it points out that what it essentially is saying is in order to get to a fraction of the points that you want to get to, a 10% fraction, just to keep things consistent, you have to extend greater and greater into the totality of the axis along each dimension. That's why you say that's kind of equivalent to saying that the points are near the edge. But what it is actually saying is in order to get the same fraction of the points that you used to get in lower dimensions, you have to stretch in every dimension to encompass a very large fraction of each dimension.
Yeah, Srinivas, I get that explanation. You're saying you need to kind of increase the volume of that space you're in, right? But at no point in that explanation do we say that as we increase the volume, the percentage increases very slowly, and only when you start reaching the edge, does it suddenly blow up and you get like a lot more of the points in, right?
No, it just says that you have to encompass, which is why I don't like the edge-oriented way of explaining it. Though it's complementary, as Joseph said, but I prefer you have to go to greater or extend your reach along each dimension to cover greater and greater portions along each dimension to just retain the 10% of what you were aiming at, the same 10% that you got by at, let's say, dimension 1. You already saw that when when we went from 1 to 2, right there, you only got like 0.1%. So that's where the rest of the calculation that we didn't go through from the link, it shows you that you have to stretch in order to retain or access the same 10% of examples that you want. You have to access more and more along each dimension.
So another way of saying what you just said, Srinivas, is that if you are relying on a distance, you're relying on finding a sample of points. Suppose your problem requires that you need points that are within, let's say, a Euclidean distance of 0.1 of something, right? Well, if you use lots and lots of features in your problem, and say if you have 100 features, it's going to be really hard to find points that are that close, that are within 0.1 of a given point. So now, in order to get those points, that you need for your training, you're going to have to relax your standards, and you're going to have to allow the distance to go out to 0.5 or something in order to get enough samples. And that's a poorer quality sample because now these points are farther away. They're not pure in the sense of being really, really close. I don't know if I'm making myself clear, but that's another way of saying what Srinivas just said. In my problem that I had to do, I was looking at a 5-dimensional space of stellar characteristics. And the characteristics were mass, radius, temperature, and a few other, surface gravity. There was one other one that I can't remember. And so if you imagine, like, I needed to find all the stars in my database that were near the sun in their five parameters, right? I don't get to choose. The sun isn't necessarily near one of the edges. In fact, it's not near the edge of the space. But I need points that are near the sun. So it doesn't help me that 99% of the points are near the edges. I need points that are near the sun, and the sun is at some random point, and they're not even a random point, but it's not near the edge. So
what are the edges in your data set? What would the parallel be like? Would that be like radius starting from minimum to radius maximum? Is that considered like an edge? Or what would the parallel for an edge be here?
The edges would be like the points that are, so if you have this 5-dimensional points, the edges are the ones that are farthest away from the origin in some sense, right?
Okay.
So with a Euclidean distance that's far, and in 5 dimension, the Euclidean distance is just, it's the 5-dimensional Pythagorean theorem. It's just the, you have 5 terms, and you have, x minus, you know what I mean? It's like x1 squared. Yeah. It's a 5-dimensional Pythagorean theorem, and the edges are defined by the points that are farthest away from the origin.
Okay.
And to answer Gautam's point, I think, again, reading through the link that I posted, what it tries to say is you need to find points which are at the edge for all dimensions when you're trying to do that. And that's where it falls apart. So at least for my understanding, that, the approach articulated in the thing that I've, the Canon-oriented approach rather than all the points are at the edge approach of explaining the same concept. I mean, first of all, it's counterintuitive. So, but given that approach resonated more with me is the way to say it, especially the point where he indicates that if you want to kind of keep the 10% the same, as you increase dimension, figure out how many more of how far you need to go in each dimension to get even the same 10% of the points. And you find out you're covering the extreme or a very, very large fraction across each dimension.
And then in a general case, you don't necessarily have uniformly distributed points. Your points have a density distribution, which, a probability distribution, which could be, in a high number of dimensions. It could be very complicated. And you want to sample, you'd like to find the points that are the best for your, training set. And so you kind of want points that are, well, how do I say, I'm just saying that if you choose points at random, without knowing the probability distribution of your data set, you won't, you're going to get points near the edge and not points where your data lies. There are sampling techniques, fancier ones than random sampling, that keep you, that sort of direct you towards where the high probability distribution is. It's called Markov chain Monte Carlo sampling, which I don't think we're going to see in this textbook. But anyway, we're over by 15 minutes, and I don't like to do that. So shall we call it a night, and then we can comment on Slack in between classes, and if anybody has any points to raise.
Just one quick point. Andreas Muller's class at Columbia, I think we've discussed Andreas Muller before. He has a lecture on dimensionality reduction and I'm just looking through, not the lecture, but at least the slide notes. Maybe worth watching at some point too.
You'll post that?
Sure.
Great. And does that have TSNE in it? Does that have the TSNE technique in it by any chance?
I don't know. I haven't.
Okay. It'd be good to see that anyway. All right. So let's end here unless there are any comments that somebody wants to make. And we'll meet again on Sunday. Thanks, everyone.